Hi, everybody. I'm going to go over a very brief little introduction on resonance here. We're going to talk about it a whole lot more in the following week or in the week that you're doing the problem set for. So we're going to keep talking about this, and this is going to be one of those things that we're going to use the entire year for organic chemistry. So I just kind of wanted to start with a bit of the patterns that we want to be following and the rules that we need to abide by. So first off, resonance structures. It's really just a method that chemists use to show areas of electron density and delocalization in a molecule. So it's really helpful because it tells us like where something might attack the molecule to form a bond, what parts of that molecule are particularly electron dense to attack something else and form a bond. So it gives us a lot of information about the reactivity of individual molecules by defining these resonance structures. Okay, so the rules that we need to follow here, number one, we need to make sure that no bonds, oops, oh boy, let me try that again. There we go. So no sigma bonds move or break, only lone pairs and pi bonds are going to participate. So what you should use as a hint for that, look for sp2 and sp hybridized atoms, okay? So those are going to help you kind of guide where that resonance can possibly take you and where you can kind of imagine that electron density flowing throughout the molecule, okay? Second rule that we need to follow, no atoms move, okay? So atoms are going to stay stationary in their positions, only electrons are going to be the thing moving. And in those electrons, it's really only lone pairs and pi electrons, okay? Rule number three, we're never going to exceed the octet on second row elements. So that's like boron, carbon, nitrogen, oxygen. Those are all going to stay at 8 electrons max. You can exceed the octet on third row. So once you get to something that has something like phosphorus or sulfur, you can exceed the octet on those. It's fairly common. That's how we get sulfuric acid. Obviously, that sulfur has more than 8 electrons around it. But for these elements, we're not ever going to be exceeding the octet there. And then our last rule, the overall charge of the molecule does not change through the resonance structures that you draw. So if you start with an overall neutral molecule, every resonance structure that you draw to kind of show different areas of electron density, those are going to be overall neutral as well. You might be adding formal charges. So it's not that you're never going to be drawing formal charges ever. It just means that whatever you start with, all your resonance structures have to match that overall charge, okay? Overall neutral stays overall neutral. +1 stays +1, okay? And we'll see what that looks like. So the other thing that we need to talk about are arrows. So arrows are such a huge part of organic chemistry because it's really what kind of visualization we use for bond formation, electron movement, and all of those things. So instead of just kind of the two things happening and then they go to product, we really are going to start showing how those things occur, like where electrons are coming from, where they are going, what we're forming bonds between, okay? So you're always going to have some sort of curved arrow like this. They're called curved arrows. We're going to use ones that have the full double head. In second semester, we will talk about some different ones there. The tail is going to be the side that doesn't have the arrow on it, and the head has the little point, okay? So our tail is where the electrons are coming from. Okay, so the tail has to start at some kind of electron that can move, okay? So in the case of resonance, we're going to be looking at pi bonds, we're going to look at lone pairs, okay? The head of the arrow is where the electrons are going. Okay, so that's going to be somewhere where they can actually fit, right? So you can't just like load them onto something that already has a full octet with nothing else to move. It has to be a place where you can put those electrons without breaking any of these rules above, okay? So the other arrow that we're going to see is this double-headed straight arrow. This is just to show one resonance structure to another resonance structure. Okay, so it just indicates, hey, these two structures on either side of this arrow are resonance structures. Okay, so just be really clear that this is the resonance arrow. It is not this. That is the equilibrium arrows that you guys probably used a lot in Gen Chem. This is the resonance arrow, which is a double-headed arrow. Okay, so I'm just going to scooch this a little bit so I'm not so crammed. Okay, so there's 4 main patterns that we need to focus on for this. And the nice thing is, like, once you're kind of comfortable with these 4 patterns, this is all of the patterns that you will ever use for resonance structures. You're just going to see them used with different atoms, maybe in slightly different functional groups, but at the end of the day, they're all these 4 patterns. So if you can identify these, you can do any resonance structure. So the first pattern is any pi bond that's next to a positive charge. Okay, the positive charge, and let's just kind of make this clear up here. Your tail is essentially where your negative charge is, and your head is where it's going to make something not positive anymore, right? So having a positive charge nearby means that, one, if you count up how many electrons I have around this carbon, I only have 6 at this point, right? So I don't have a full octet on that carbon, so I actually do have space for more electrons, okay? So this can take another 2 electrons. Over here, I have 2 electrons in a pi bond. So what I can do is, this molecule doesn't actually sit static like this. It actually exists more as the average of the 2 resonance structures that I'm about to draw. And we'll talk more about that average idea in class as well. So one of the things when you're drawing resonance structures out for the first time, I would really recommend just drawing all of your sigma bonds out first, because those are never going to move. So this is all of the sigma bonds that I have present in this starting material, right? I've got 1, 2, 3, 1, 2, 3. I still have 1, 2, 3, 4, 5 hydrogens, 1, 2, 3, 4, 5. I have all the atoms. I have all the sigma bonds. They have not moved. This arrow here is telling us we're going to take this pi bond and we're going to take those electrons and put them between those 2 carbons instead. Okay, so that has made a new pi bond over here, where now this carbon, if we look at it, it really doesn't think that life changed anything, right? It still has the 4 bonds. It's still got one of those bonds being a pi bond. Nothing much has changed. This has definitely seen some change, because now we've got 1, 2, 3, 4 bonds instead of 1, 2, 3. So now this is no longer positively charged. And this one also felt some change, because now I only have 3 bonds, and now this one is positively charged. Okay, so essentially what this is looking like is we just have kind of delocalization of electron density between those 3 carbon atoms. Okay, so they're essentially, like, I always do a Lord of the Rings reference here, but they're sharing the load of that positive charge, right? So we've got these 2 are both kind of holding the same amount of positive charge. It's not just one or the other. They're both bearing that weight, okay? All right, so let's look at the next pattern. So for the number 2, a pi bond that's shared between atoms with different electronegativities, okay? So the different electronegativities part is key. This is not something that just happens on, like, an alkene that has 2 carbons. You'll end up drawing a lot of wacky business if you do that. You're really looking for different electronegativities, okay? So in this case, oxygen is quite a lot more electronegative than carbon. And the carbon is less electronegative. So if you're trying to think about which one of those things is more likely to steal electron density from the other one, it's definitely the oxygen, right? It's more likely for electrons to flow that way, and that's just what a dipole would look like. So that's the same direction that we're going to go with our resonance structures. So again, we're looking for a pi bond. So I've got 2 pi electrons there that I can just take that bond and put it up onto my oxygen. Okay, so the tail is coming from the pi bond, and the head is going exactly where I'm going to put those electrons. In this case, I'm putting them on an atom. In this case, I was putting them on to form another pi bond. Okay, so it depends on if you're pointing the arrow to a bond or an atom in terms of where you actually want it to end up. Okay, so then that's going to look like this. So again, we start with all of the sigma bonds. Those aren't going to move, and all the atoms don't move. So now let's count up how many lone pairs I have. So I started with 2 lone pairs on my oxygen. That arrow actually added a 3rd lone pair. And this carbon down here now only has 6 electrons around it. It's now got a formal charge of +1. My oxygen up here has a negative charge on it. So these 2 things are resonance structures, okay? And what this one is telling you specifically, it's saying, hey, look at this carbon. Something could come that has electron density and attack that carbon because it has a partial positive charge on it, okay? So that's the kind of information that we're getting out of this. Alrighty, so pattern 3 is any lone pair next to a positive charge, okay? So if I've got lone pairs right here, and I've got a positive charge right next to that, then again, just like we saw up in this one, right? We have not a full octet. We have some electrons that could help that out. So we're going to end up seeing that occur. So in this case, instead of a pi bond, I'm using a lone pair. And we're just going to take that lone pair and we're going to put it into a new pi bond. Okay. So again, my tail is coming from the lone pair and my head is going to that bond to indicate that I'm going to form a new pi bond. Again, we're going to start with all of the sigma bonds in place. We now have a new pi bond right there. And we still have 1 lone pair on my oxygen. So now if I'm calculating formal charge, this oxygen valence of 6, 1, 2, 3, 4, 5 owned electrons. So that's going to be a +1. Okay. So if we look at this, I started out +1. I still have overall +1. We're good there. It's a nice little double check to make sure that you did things correctly. So we can use lone pairs, we can use pi bonds. We've got options around, okay? Alrighty. So then number 4 is a lone pair next to a pi bond, okay? This is gonna be the first time that we're gonna see 2 arrows in action, and you'll see why in a second. So again, I've got lone pairs here, and I've got a pi bond next to it. So this is not lone pairs on a pi bond. This is lone pairs on an atom next to a pi bond, okay? Because essentially what I can do is I can take that lone pair and make a pi bond right here. But what happens if I do that? I'm just going to draw that out really quickly here without anything else. Okay, as soon as I do that, I'm going to make a really sad little situation here. Okay, that carbon has how many bonds on it? It's got 5 bonds on that carbon. So I've got 1, 2, 3, 4, 5. Even in an intermediate type of state, I cannot do that. Okay, so we are not going to have that. No 5 bonds to carbon. Okay, so if I do this one arrow, something else has to move. Okay, and that thing is going to be our pi bond that's right next door. Okay, so if I have this, I can just move that pi bond onto my adjacent carbon. Okay, so if I draw out that, again, we're going to start with all the sigma bonds. And then we're going to follow our arrows and see what they tell us. So this arrow, we're taking one of those lone pairs. So now we only have 1 lone pair on this oxygen. Make that bigger. Okay, 1 lone pair on that oxygen, and the other one became a pi bond between the oxygen and carbon. okay? And then this pi bond, we took that and we put those electrons on the carbon as a lone pair. Okay, so now we figure out some formal charges. The oxygen is a valence of 6. It owns 1, 2, 3, 4, 5. So that's a +1. The carbon is a valence of 4. Right now it's owning 1, 2, 3, 4, 5. So that's a -1. Okay, so you can see how we started off with neutral. Plus and minus together makes neutral. So this is our resonance structure of this original one. Okay, so it just shows you that because that electron density is kind of shared through this 3-atom system, this carbon here is actually more electron dense than you might expect it to be, okay, because these systems are connected. So again, it kind of helps us to identify some of the reactive areas in a molecule. So we're going to be using this a lot in the next year really. And we're going to look at some more complicated examples because these are pretty simple ones. And we're going to start out with some simple ones, but you can see in bigger structures, resonance structures that are very, very involved in terms of how far you can delocalize certain areas of electron density. So the thing that you want to keep in mind, just as a summary here, make sure that you're not exceeding any octets. So make sure that as you're starting out, drawing in H's is going to be really helpful to make sure that you don't put anything onto an sp3 carbon, for instance. Make sure that you keep octets on oxygen and nitrogen. If you look at all of these, they all have something in common in that they still all have 8 electrons. The only one that I've drawn as a positive charge has been carbon, in terms of 6 electrons and not a full octet. And then just keep practicing with these patterns. You can do whatever you want to in terms of labeling them. Like if you want to be able to say like, okay, this is an A, B, you know, you can do a bunch of different things to try to find those patterns. But we're going to keep working on this for a little bit, and let me know if you have any questions and we will talk again soon.